obviously, I still don't have the project proposal up, my apologies for that, but it will happen when it happens, you know what you need to do in any case. I'll be out of town, flying out tonight, won't be back till Monday, so, I'll try to stay in touch on the Slack, but if you don't see me on the Slack, it's because I'm in Boston with limited internet connectivity, sometimes it's live, so apologies for that in advance. Anything else to say? Please don't panic if, as far as the accessibility of your repos for homework one, I haven't cloned them all yet. I will the next day or two, but, you know, in the meantime, don't worry about it. If I can't get at your repo when I go to get at it, I'll drop you an email or a note on Slack and we'll figure it out. It's not that big a deal. Let's see, what else? That's all the what else. Anybody else got anything we need to talk about before we start talking about Rust again? Yeah. Soon. Yes, there will be a homework 2 and a homework 3 and a homework 4 is the plan. I plan to have 4 homeworks in the 6-week period. That's my goal. Yeah.
When will homework 2 be due?
Sometime a week or 2 after it's handed out. I'm not going to give you anything with a short fuse. Yeah, the next class period. No. We'll try to space them out in here. I know you're all working on projects as well, but last time I taught this course, I didn't give enough homeworks, and I feel like some people really need to be motivated. It makes me sad, but I really feel like some people need to be motivated by actually being encouraged by homework to engage with the material to figure out some of the topics. You know, don't be that person. Just go learn Rust. It's not that hard. There's a really good book, and we talk a lot about it in class. But you know, we'll still have some homeworks to do. That was probably the last homework. Homework 1 was where I'll give you code for it. And so part of what I'm thinking about is how to structure the next homework so that it's reasonably gradable. And still, we'll give you stuff that you probably need to know at this point. Of course, there's a certain amount of these first couple of weeks trying to get you through enough material. And really, next Monday's lecture as well, trying to get you through enough material so that you can write Rust programs intelligently that look like computer programs. You'll notice that first assignment, I was really careful to make it stuff that could mostly begin with floating point numbers. That gets boring really fast. I mean, homework 2 is not going to be Celsius to Fahrenheit and Fahrenheit to Celsius. And in fact, what I want to talk about today, which is some more stuff about references and lifetimes and arrays and that kind of stuff, is all about getting you to that point where you can sort of get back in Rust to where you are in C or C++ or Java or whatever, Python, whatever it is. You know, sort of get you the basics of the language so you can write programs with strings and arrays and, you know, pass things by reference and do all the stuff that you sort of expect to be able to do in even the simplest computer program. And, you know, so that's sort of the focus. That's the focus today. That's the focus on Monday when we talk about structs and enums, I think. And once we have that, we'll have talked about strings and arrays and structures. And once you've talked about strings and arrays and structures, as far as imperative languages goes, and functions, which we've kind of talked about already, you kind of talked about all the things that are absolutely necessary to write reasonable, simple programs. So that's always a good goal to get to. So that's where we're going today. So let's review what we did on Monday this week, which is we talked some about, well, there's all this stuff about the stack and heap. I'm not going to say much more about that, but this idea of memory allocation, copyable values, blah, blah. You know, it's all about at some point understanding that at some point for every value program, it's always got a primary place where it's living right now called the owner, right? At runtime, there's always a place you can identify where you're like, at this point in the program, this variable will statically live in, whenever you get to this spot in the program at runtime, this value will be living in this variable, right? Whether the variable is part of an array or a structure, or it's a standalone variable or whatever. And that's the thing that's the owning location of that value. And if a value ever finds itself without an owning location, then the next thing it's going to find is the compiler is stuck in code to free that value. And so values are allocated when they come into existence and are initialized. And then they travel through your program, however they're going to travel, and then eventually they become unowned and are, garbage collected by code introduced by the compiler at the compile time. And that's sort of the Rust magic here. We talked about moves a little bit, which is this idea that it doesn't always have to be the same owner. You can have a thing owned by X here, and then you can have it be owned by Y after that, but once Y doesn't owns it, X doesn't own it anymore. So that bogus value, which is just some value, it doesn't really matter what it is. I often do that empty struct thing in these kind of examples because empty structs aren't copied, which is, it can really confuse you when you're thinking about ownership to think about the copy types, which is something we talked about, right? If I said derive, clone, and copy up there for bogus, then this example would compile just fine, because when I said let y equals x, it would just make a copy of the value, and now y would own its copy of the value, and x would own its copy of the value, and the compiler would be perfectly happy with that. And almost all the standard types are copy types. The number types are all copy, unit is copy, sort of everything's copied. Strings aren't copied, but string references, pointers are copied. And so with everything being all copied, you kind of got to pay attention to that, using an empty struct like this sort of highlights the fact that sometimes things aren't copied. Think of bogus as actually being a struct with 50 fields, including a giant array, and that makes this example makes more sense. And I really do expect today, like we're good about on Monday, lots of questions. This is probably the most confusing and difficult stuff in Rust that we've talked about Monday and are talking about today, because it's so unfamiliar. And so please don't hesitate to be confused. Say, I'm confused, and we'll try to sort it out. That's part of the fun. So, yeah, notion of ownership, super, super important. And we talked a little bit about the fact that if you own a thing, you can decide to change it, right? That's part of the joys of ownership, is the ability to make changes. The compiler insists that you mark it as I intend to mutate this with the mute keyword. And once you've done that, the compiler's like, sure, mangle away the thing. So far we've mostly talked about, there again, about concrete values. One of the hard decisions scalar values, one of the hard decisions that I had to make for this week that I think I mentioned before is, do I talk about arrays and vectors and strings and stuff first, so that we have a bunch of collection types that we can talk about, because a lot of these ideas become more interesting with collection types. Or do I talk about ownership first? I decided this time around to talk about ownership first because I sort of feel like if you can master ownership for these simple types, borrowing for these simple types, you can do it for really fancy types too. So tied up really closely with the idea of ownership is the idea of borrowing, which we've talked about, I think. I can always say ampersand some owned value, and now I've got a reference, a pointer to that value. It may turn out to be some kind of smart pointer with a length or something buried in it, but it's still basically just a pointer. I can also say ampersand mute, meaning I want a pointer through which I can actually change what's being the stuff, the contents of the thing being pointed to. And of course, to get a mute pointer, I have to have the thing be mutable, that I own be mutable to begin with. And really, the only way to get a pointer or a mute pointer, to get a reference or a mutable reference, is to either own the thing, so you can take a reference to it, or to get a copy of one that somebody else had. You can always get a copy of somebody else's immutable reference. So there's a school of thought in the Rust education community, which yes is sort of a thing, that mutable and immutable were terrible names for these concepts, for these references, that the right way to think about them is as shared references or exclusive references. What we talked about at the end of class last time is that if I share, if I can make as many shared pointers, immutable pointers, as I want to a value I own, I can hand them out to everybody or whatever. I can't mutate the thing while I've handed out immutable pointers to it, but I can use it too. Everybody shares. If I make the thing mutable and hand out a mute pointer to it, then the person who owns that mute pointer is the only, the thing that owns that mute pointer is the only thing that can change the value until that mute pointer goes away. It has exclusive, non-shared ownership, sort of borrow of that value, not ownership. I still own it, technically, but I can't do anything with it except to wait for the borrow to go away.
So clarification, like, just making sure that I'm understanding this correctly. An ampersand is just saying that, hey, you can read this. And an ampersand mute says, hey, I'm giving you rights to write this.
Absolutely correct.
And this is not messing with or writing up the pointer itself, but the thing in the pointer.
The thing being pointed to,
Okay,
correct.
wonderful.
Correct. Yeah, you can always sort of do whatever you want with the pointers themselves. They're, well, you can't really, because you can't make a copy of a mutable pointer, for example, because if you did, then what would that mean? But for shared pointers, you can make copies of them and do all that kind of stuff. You can't really change their addresses, because unlike C, Safe Rust doesn't have address arithmetic, so I can't ask for the pointer to the next thing in an array, for example. If I hand you a reference, an immutable reference to an array, in C that would be a pointer, right? Ampersand A, and now I'm like, well, I'll add 1 to that pointer, which really means point to the next element. There's nothing like that in Rust. Rust is like, no, you can't do things that way. And so when we talk about arrays and strings later today, that'll be clear. Yeah, great question. Somebody else had a question?
You don't have to dereference references with pass, right?
If you want to use the contents, you technically do have to dereference references you pass. One of the things we talked about last time is that there's a whole bunch of special cases where the compiler does that invisibly for you, which is really super annoying and confusing when you're trying to teach the language, because it's like, well, you didn't put a star in front of that, but the compiler puts stars in front of it for you sometimes, but there always should be a star there. So if let's actually make this concrete. Concrete's always a good thing. So let's not use struct bogus here. Let's use something that actually has some, so that I can actually mess with. Let S be some string. And we'll talk about more about the differences between string and str or whatever. If I say let t equals ampersand s, let u equals ampersand s, then I can certainly say print star t, print star u. and that program should compile and run as far as I know. Hello, hello. You know, that's perfectly legit. If I leave off the star, it turns out that because of the way the println macro works, and because of something called the ref and deref trait, as ref and deref traits, which we haven't studied yet and won't study for another couple of weeks, the compiler will be happy to stick the star back on for us so that everything works out. The secret here is that println's about to take a reference itself anyway to its argument, and so ampersand star kind of is self-canceling, but there you are. So, yeah, macros are magic, deref and asref are magic, and so there's a bunch of magic going on. But in the simplest form, that's the program you'd write, right? I can certainly say things like, that's what I was gonna say. So if I make this mutable, I can make this a mute pointer, a mute reference, and I can say s or t plus pointer to t plus equals bang, and that's perfectly cool. Now notice this won't compile. Why won't this compile?
Because you have a reference.
Oh, because U is trying to take a shared reference to something that already has an exclusive reference out, right? All right, so we need to get rid of U to make the thing compile. That sounds like the first step. And so let's get rid of U, and now let's print the pointer to S and the pointer to T. Will this compile now? Why not?
You can't access S.
Oh, because while I've got a shared reference, while I've got an exclusive reference out to S, I can't access S itself, so that's not going to compile either, right? So you're starting to see what the rules are, right? And you sort of see the why of the rules in that, you know, you want to know when you're changing things. I could do this. I could also write this. Now my mutable reference is gone, right? Now I can println S, right? Because now I don't have a mutable my exclusive reference that I gave away, I got rid of, and so now I'm actually happy to be able to mess with my own value. Because after all, I own that value, yeah.
I must be misunderstanding what star means. I thought that star meant like, once I give this to you, let it go so that somebody else can see it?
No, star's just a pointer dereference like in
Okay.
C or C++.
Okay.
It's absolutely just, I gave you an address, I want to talk about the thing at that address, and so star address is the thing at that address.
I thought that that was what and did.
Ampersand gets an address of a thing, right? So they're inverse operations in a sense, right? Ampersand S would give me the address of a thing. So it's a number that represents where that thing is in memory. Star T, right, says give me the thing that's at this address in memory. So they're sort of inverse operations of each other. This is the C++ thing.
And is the address, and star is the thing at the address.
Yeah, absolutely.
Wonderful.
Absolutely. Although, like I say, the address in this case, because it's Rust, might not be just an address. It turns out that a length might be part of it or something else. Yeah.
Here you have star S. But as self.
Oh, sorry.
necessarily-
That star S is wrong. It won't compile. Thank you. It's like, oh, it's just not. That's not a thing. Thank you.
That's what I
I
thought.
think that was like a special rule.
No, the special rule here is try and actually compile your code to see if it will compile. It says, oh right, immutable borrow occurs here. Oh, dropping T is not sufficient, right? The problem is the drop operator actually gives up ownership of T,
So now nobody
but
owns
it
it?
still is lexically in scope, and Rust uses these lexical scoping rules. So to get it to actually take T clear out of lexical scope, I have to do this instead. So now everything's going to compile and run, and it'll be perfectly happy, assuming that the internet works and that the playground isn't overwhelmed and that kind of stuff. There we go. Hello, hello. And notice that, the S that I print at the end absolutely has been changed, right? It was changed through that exclusive reference I gave out to it. That gave the reference to the power to change it, and they took advantage of that power. So much personification of programs today. And so when I get back, I find out that, well, you gave me the right to edit it, so I edited it. Go away. It's fine. Yeah.
So if after the print line where you call the reference that T's pointing to, if you put in the drop T there, then it wouldn't compile, right? Because you've dereferenced that memory, basically?
No, the println doesn't do anything. The only thing that happens is, oh, you mean after the curly braces? Or?
No, before the curly braces ends.
Yeah, the println doesn't do anything. It just shows you the thing.
Right, but if you add drop,
Let's see what the drop T does when I do it. I'm confused whether drop T drops the pointer or the value pointed to, so maybe you're right, maybe it won't compile, but I kind of feel like it will. I know it will. I'm quite confident it will. No, the drop T there just drops this. Drops the variable T, which is just an address, just a reference to a thing, and so that doesn't affect anything.
What if you do a drop star T?
Then I think it will complain that I can't move, right? So remember how drop works, right? It drops the thing by moving it into the parameter, and one of the things I'm not allowed to do is move around a thing that I only own a reference to, right? I can't. Even having a mutable reference, even having an exclusive reference, doesn't give me a right to move the value around. The owner still is the only person who can move the value around. And so what I'll get at this point is a compiler error that says, no, you can't be moving that stupid value. That's not a thing, because you don't own that value. Go away. And so the drop will fail to compile. If I drop S at that point, which I can because it's in scope,